Hi, and welcome to the virtual version of the Geometric Optics and the Human Eye Lab. I realize that you may not have learned about optics in the lecture part of your course, so we're going to start out with a little bit of background on that to make sure that you're oriented. We often use two idealized light sources in physics, the laser beam, which we'll talk about in a minute, and the point source. As an approximation to a point source, I'm going to use this, which is just a light bulb, and it's shining out through that hole. Looks really bright, but inside of there is just a regular light bulb. It's not truly a point source because the filament inside the light source has a finite size, but it's a pretty good approximation. I'm going to shine the light from it across this whiteboard, and in order to see that, I need to turn out the lights in the room. I'm also going to move the camera to an overhead view like this. Okay, so in this view, this is our light source here. It's a little bit above this whiteboard and it's tilted downwards. So it first hits it about here, and you can see that the light is diverging away in this pattern. I'm just going to mark it. If I mark these straight lines, coming out from it, they're basically rays that are diverging away from our point source on the left. So even though we have a continuous beam of light coming out from here, it's helpful conceptually to envisage this as being made up of rays of light that are emanating out from the point source. So if I were, let me just erase this. If we think about, let's say, if we move our little point source here, we can imagine that there are rays of light coming out from it, going out in all directions like this. So that's an idealization of a kind of source of light, but in practice we can approach that quite closely. For example, when you look at the tip of my nose, or let's pick something even sharper, the tip of this pen, what you're seeing is light that strikes the tip of the pen, and then the tip of the pen is acting like a point source and radiating light in all directions out from it. So if we consider something that's very sharp, in reality we can get as close to a point source as we would like. Another idealized form of light source is the laser. You've all seen laser pointers. Here I've got a special kind of a laser pointer which has actually 5 lasers built into it, so you should never look into a laser, but it's safe under these circumstances for me to have the laser point straight into the camera. These particular lasers have got a lens in front of them so that instead of just a beam of light coming out, there are sort of fat slits, sort of fat segments of light coming out. So I'm pointing this straight down at the board, and that's the shape of the light that's coming out. One of the very useful properties of a laser beam is that it's essentially free of the divergence that we saw from the point source. Let me turn off the lights, and I'm going to put this source over here. The laser beams are directed slightly downward so that they graze along the whiteboard here, but I need to turn off the lights for you to see them. Okay, again, the source is designed so the lasers are shining downwards so that they only first strike, you're looking from above. So the lasers start a little bit above the whiteboard and they only really strike it at this point. But you can see as they move across, there is no divergence. They just go in straight parallel lines, and each line is of constant width. For the next part, I want to see what happens with just a single laser beam, so I'm going to use some tape to cover up all but one of them. Okay, so I've covered up 4 of the 5 laser beams coming out, and so there's just this one left that's coming out, and I've got a block of plexiglass here. I'm going to turn off the room light so you can see the beam Actually, let me just redirect them. Yeah, that's perfect. So now you can see the beam, and it's going straight into the block of plexiglass and straight out the other side. So when I start to tilt the plexiglass, you can see that the beam, the direction of the beam gets changed. I'm going to move you so you have an even more direct, straight overhead view. It's about as straight overhead as I can get. So there's straight on, the beam just goes straight through, but when I tilt it, you can see, let me move this a little bit further this way. So here is the path that the beam would have gone on, straight across like this, but instead it gets bent this way. So that's the process of refraction, and to understand that, we use a line that is perpendicular. So there's two refractions happening, one at this surface and one at this surface. Let's concentrate at what's happening at this front surface. And by the way, just so you don't get distracted, you can also see that there's a reflected ray. So here's our incident ray here, and then there's also a reflected ray over this way. But that's not the thing that we're mostly paying attention to during the lab. We're talking mostly about refraction. So to understand this refraction, I'm going to introduce a construction line which is perpendicular to this front interface. So it's about like that. That's called the normal, in the sense of the word normal, meaning orthogonal or perpendicular to. So that's at a right angle to this interface. And you can see that the beam, if it hadn't been refracted, it would go this way. So it's being bent toward the normal. I can extend the normal out in this direction on this side, and we could define the angle here to be, oh, I got to draw this upside down for you guys, theta sub 1. Let me label that a little bit better if I can. This marker is not cooperating, so I guess I'll use this one. So this is theta sub 1. And so that's the angle of the incident beam relative to the normal. And then this angle here is the angle of the refracted ray relative to the normal. So that angle, the angle of the refracted ray relative to the normal, that's theta sub 2. And Snell's law relates theta sub 1 and theta sub 2, and it says that the angle theta sub 1 is related to the angle theta sub 2 by the relationship n1 times the sine theta 1 equals n2 sine theta sub 2. In this equation, n1 is the index of refraction of the medium on this side, which is air. Air has an index of refraction of just about exactly 1. Vacuum is exactly 1. Air is very, very close to 1. N2 is the index of refraction of the plexiglass, which is, I haven't looked it up, but it's something bigger than 1. So 1 is the minimum value of the index of refraction. The index for plexiglass is probably about 1.5. So again, what we've learned so far is that when you're going from a medium with low index, like air, to high index, like plexiglass, the beam bends toward the normal. And the equation is given by Snell's law here. At this other interface, you can see that the deflection of the beam is in the opposite direction. So let's draw the normal over on this side. So that's meant to be perpendicular to that interface. And if I took this beam coming into that interface and tried to extend it, it would go about like so. And so you can see in this case, the beam is being bent away from the normal. So when you go from high index like plexiglass to low index like air, the beam gets a bent away from the normal. Both of these refractions are described by this same equation. So, for example, on this second one, this angle here, that might be theta sub 2. Theta sub 2. And then, let's see, here's the normal for this ray, so this angle in here would be theta sub 1 for this second one. So we just use the same equation for both refraction events. You got to keep track of which medium you're calling medium 1 and which medium you're calling medium 2. Okay, you could see it from Snell's law, but I also wanted to show it to you experimentally. Let's concentrate on the refraction of the first one, that the bigger I make the angle, the more the ray is deflected. So at 0 angle of incidence relative to the normal, it's not deflected at all. And the bigger I make the angle relative to the normal, so I'm constantly moving the normal, so it's farther and farther away from the incident beam, the more the beam is getting refracted. And so that's the basis for how we make a lens. So I'm going to uncover the other 4 laser beams to show you the principle of action of a lens. So now we've got all 5 laser beams, and I've got this piece of plexiglass which has a circular part and a flat part. And let me put it in here, and so you can see what happens. So this central ray strikes, let me put that right at the middle of the lens. So it strikes the middle and just goes through undeflected. As we go to one side or the other, the angle of incidence relative to the normal is getting bigger and bigger, and so the rays are being deflected more and more. So for example, right here, the normal is maybe about like so. Here, the normal is maybe about like so. So this ray has got a bigger angle relative to the normal than this one does, so it gets bent more. And you can see that the net effect is that all the rays come to pretty close to a point here. Let's see if I can zoom in on that place where they're coming pretty close to a point. I got to move you over there. Hopefully what you can see is that they're not quite coming to an exact point. They're just coming pretty close to one. So that effect is called spherical aberration, and that's because I'm using a lens that has a circular shape to do that refraction, to do that converging of the rays. It turns out that it's easy to make lenses that have circular surfaces or spherical surfaces for a normal lens you'd use in 3 dimensions instead of this kind of funny 2-dimensional setup. And a spherical surface is an approximation of the surface you need to focus parallel incoming rays to a point, but it's not the exact shape that you need. The exact shape is sometimes they do make lenses with that exact shape. They're called aspheric lenses, and they're considerably more expensive than normal lenses that have that spherical approximation to the ideal shape. So for the purposes of the rest of the lab, we're going to mostly ignore that spherical aberration and just think of the lens as something that has the capability of taking parallel incoming rays and converging them to a point. The distance from the lens to the point at which they converge is called the focal length, abbreviated f, little f. And we are, in the context of this, this lab, we're always going to be using the thin lens approximation. So that is, we're going to be thinking of the lens as having very small width in this direction, even though obviously for this lens, that's not a very good approximation at all. So the focal length, again, is defined as the distance it takes for a lens to converge incident parallel rays down to a point. it also would work the other way. So if this were a point source and the light were coming this direction, the lens would converge these rays that are coming out of the point source into parallel rays. So you can see that the shorter the focal length is, the more converging power the lens has. So I'm going to put in now this other lens, which has a smaller radius of curvature, which I believe will correspond to a shorter focal length. Let's see if it actually works. I'm going to put the flat end at the same place, try to get it centered, and you can see, yes, now the rays are being approximately converged there. So the smaller the radius of curvature of the lens is, the shorter the focal length is, the more converging power the lens has. As you may have read about in the pre-lab reading, the power of a lens, which has units of diopters, is defined as 1 over the focal length in meters. Most of the time when you're dealing with lenses, we talk about the focal length, but when you're talking about eyeglasses, they are usually quoted in diopters, and sometimes it's more helpful to think about lenses in terms of diopters. Okay, the lens that has this shape is called a plano-convex lens. We can also have a double convex lens like this one. Let's compare the focusing power of this one with the one that we have. You can see when I compare them that the radius of curvature of this one is much bigger than for this, but on the other hand it's got two surfaces, both of which are going to tend to converge the beam. So when I put that one in, maybe you can see that the beams are starting to converge as they go through this first curved surface, and the second curved surface is converging them even further, but they don't converge to near a point till out here. So this one has the longest focal length, or the weakest focusing power, and then this big one is second strongest, and this is the strongest one. Now let's see the effect that these have on our point source. Okay, I've replaced that array of 5 laser beams with the point source that we used before, and I'm going to start by putting in the weakest of the 3 lenses. And you can see that just about takes this light that was diverging and converges it into an essentially parallel beam. Notice that if I move it closer to the source, like so, now it's no longer able to make that convergence, so that the beam that's coming out of it is diverging. It's got a cone to it. And when I move it farther away from the source, I don't know if you can see it, but now it's able to converge the light. So the light is, instead of being parallel, it's converging. So the converging power of a lens, whether it's able to kind of overcome the divergent nature of the source, depends on how far away from the source it is. And in fact, as you may recall, when I get this so that it's 1 focal length away from the source, that's when the outcoming beam is parallel. So now the distance from here to my source, which is just barely off screen, is equal to the focal length of this lens. Let's now try the similar thing with our next most powerful lens. I'm going to put it at about the same point, and you can see that it's converging it here. I can move this one closer into the source. So about there, I'm hitting the legs of my tripod. Somewhere about there is where the outcoming beam is parallel, and so this would be the focal length from the center of this lens to our source would be the focal length of that one. And then finally, for this one, I could move it even a lot closer in before it became parallel. It'd be about like that. So again, this is a useful way of thinking about lenses, is in terms of their converging power. And if they are farther away from a point source than their focal length, then they will have enough power to converge the light approximately down to a point. But if they're closer to the lens than their focal length, like in this example, then they don't have enough converging power to converge that light. So it's diverging less than it is without the lens, but it's still diverging. Finally, let's talk briefly about concave lenses. This is an example of a double concave, so it's concave on both this surface and this surface. And so when I put this in, you can see that it causes the parallel rays to start diverging. So it's the opposite of what a convex surface does. Let me move this a little bit further this way. Still not. I'm going to switch to a different lens. So this is called this is a double concave lens. This would be a plano concave lens, but you can see the radius of curvature for it is smaller. So let me put this in here. Yeah, that's good. And so so ignore these two outer beams. In fact, I'm going to tape those over. Okay, I've got those taped over now. So one way to think about the action of a diverging lens like this is to so the light is really going from this side to this side. But if you imagine sort of back projecting these three rays, they would meet at a point about here. And so we can think about an equivalent of a focal length for a diverging lens, but because the rays sort of virtually meet on the incoming side, it has a negative focal length. So this has a focal length, but it's negative. So if you measured that and expressed it in meters and just took the negative of it, that would be the focal length for this. This one has a pretty short negative focal length, whereas the double, this one, if we tried to trace these back, it would be someplace way over here. So this has a focal length that's also negative, but much longer. Okay, so now we've earned a bit of fun. I'm at home, and we're going to have a song about Willebrord Snell, the man who invented Snell's law. This song is written mostly by my wife, Marion Mackenzie, with a little help from me, and it's set to the tune Sweet Betsy from Pike. Come listen and learn, I've a story to tell. I sing of the genius of Willebrord Snell, a mathematician who lived long ago in the Netherlands where the Rhine River does flow. He set for his mind occupations of worth, improved navigation and measured the earth. He gave us the sine law, that wonderful guy, and he made more precise calculation of pi. Singing n1 sine theta sub 1, hey, 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 equals n2 sine theta sub 2, hip hooray. His greatest feat came in 1621, when optics as science was really begun. While flashes of lightning illumined his page, he wrote down Snell's law, his great gift to the age. So if you wear glasses or like to fry ants, be grateful your lenses were not made by chance. Astronomers hail him with each newfound star, microscopists toast him from each sleazy bar, singing n1 sine theta sub 1, hey, 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 equals n2 sine theta sub 2, hip hooray. Now some credit Harriot, others Descartes, both studied refraction and both were real smart, but we prefer Willebrord, Van Roy and Snell. He laid down the law and he did it darn well, singing n1 sine theta sub 1, hey, 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 equals n2 sine theta sub 2, hip